Hello everyone, welcome back to a brand new video, and today I'm finally back after a pretty long hiatus, and this is going to be part 1 of a 2-part video series on the new audio API on Roblox. So the goal of actually learning this new audio API is to be able to make advanced visualizers that work on different kinds of frequencies. Today, I'll be introducing the basics of the new audio API and what you need to know in order to use the audio analyzer, which is the object responsible for analyzing these frequencies. As you can see here, I have a list of all the new audio API objects, but they won't be available to you right away because you have to go into beta features and enable the new audio API settings. Once you enable this and click save, it will ask you to restart your Roblox Studio and make sure that you click restart, because if you don't, the audio API objects will not appear inside of any of your games until you relaunch Studio. Now it's time to actually start setting up the basic circuit in which audio will travel all the way from the source all the way to the listener's ears and the visualizer. So I'm actually going to be using multiple parts here, but this can all actually be put inside of one single part. This is just for showcase purposes, since I want to demonstrate visually what comes before what and what leads to what. The first block I've added here will represent the source, so I'll call it that. As for the second part, we're going to make the audio output, which I'm going to call output. I'm going to color it white to make sure we can differentiate the two. So the way this works is pretty logical. The audio is created under the source block, and then the audio is passed on all the way to the output block. Although right now we have nothing creating the audio and nothing receiving it. So we'll add an audio player inside of the source block. If you've already used the previous sound object, you'll be familiar with some of these properties. In our case, we're going to keep looping enabled, and we'll keep isPlaying disabled for something that I'll show later on. Now to actually insert the audio, we'll go through the same process as before and get the asset ID from the Roblox audio library. Although in this case, the important part is to add rbx asset ID : / before the ID. You can confirm if it worked if the time length changes to something other than 0. Now if I hit play right now, you'd think that, oh, we have an audio now just like it was with the previous sound object, but no. The way the new audio API works, you need an output for this, which is why we created the output block. So we already have the audio player, but to actually receive that audio and play it out, we'll use an audio emitter. Through the new audio API, the input and output are separate, which means that you can actually have as many outputs as you want. You can have the audio playing from multiple different places by just duplicating the block and connecting the two emitters to the same audio player. However, since we're making an Aura, we don't actually need to have more than one audio source, since we just need one at the center of our player. Now that we've established the basic points of our circuit, we actually need to connect them somehow, because these things don't have any properties that you can use to connect them, so we'll be using an object called a wire to connect the two. This is similar to real life, how you'd connect your computer to a speaker through a wire, and then the speaker will play the audio coming from the computer. In this case, we'll place it under output, and I'll just name it something simple like source to output. To actually set up the wire, you're going to pick two different instances. One is going to be the source instance, which is where the audio is coming from, aka the audio player, and the target instance, aka the audio emitter. Now in theory, you'd think that we already have everything in order to make a proper circuit and have our audio play, so let's test out if that theory is true. Since I didn't cut the music here, I'll just tell you there is no audio playing. So the first of two reasons this actually didn't work is because we did not play the audio. If you remember earlier, I left the audio player's settings is playing to off. And that means we're going to have to enable it somehow. So before we get to scripting, I'm going to group this into a folder. Then I'm going to add a script that will activate the audio player and make it play the audio. Make sure the run context is client as usual. Now the line of code we need to write is pretty simple. So we're just going to access the audio player first of all. So we'll go script.parent, which will bring us to the folder, .source, which will bring us to the source block, .audio player, which will bring us to the audio player himself, and then we're just going to add :play. Once again, this is why I kept isPlaying off earlier, because keeping it on will actually bug things out, and you're supposed to enable it using a script. There's also the stop option in case you want to use this in a different script, but in this case we'll just keep it under play. Now if we test this again, this should work in theory, but also keep in mind I said 2 reasons it didn't work. In this case, there's actually one thing left to do, and that's to actually create the object that'll be listening to this audio. Because right now, we have a source, we have something that emits the audio, but we have nothing to actually listen to the audio and bring it to our computers, so we can hear it ourselves. So we'll be making a second script with a run context client, so we can code something else. To add that last missing component of the circuit, we have to go into the script and add a listener object. We can do this by simply adding an instance.new audio listener. Now an important part of this, you have to make sure that this is parented to the camera because we want it to follow around our player. It's going to act like the ears to our player. The next step would be to add a wire that connects this listener ear over to something that will actually output the audio on our computers. So we'll just make a brand new wire with the same instance.new function. In this case, the wire is going to act like the neurons, connecting the audio that we receive from our ears over to our brain. Also, don't check if that's scientifically correct because I'm not sure, and frankly, I don't want to know if it is. As for the brain part itself, we're going to have a third brand new object that's going to be the audio device output. If you couldn't tell from the name, it's going to take any audio that's brought to it and output it to our device. Don't forget to parent the wire and the output to the listener just so it's easier to access in the future. The last part of all of this is we have to actually connect this, since we made the wire but we didn't actually choose the source object and the target object. So let's just do that with wire.sourceInstance equals listener. And then we'll set the target instance to the output, aka the audio device output, which will bring this all to our computer. One quick thing to avoid any errors at all, we'll just go back to our first script and change that .source statement to a :wait for child source. Now if we just test it, we should have a working audio emitter. Now if I just walk around this object right here, you'll notice that the sound is actually spatial, which means that it's happening in multiple dimensions and not just coming out of our ears in the same volume no matter where we are inside of the workspace. Basically, we got surround sound audio. Now we finally got the base circuit working, but now you may be asking yourself, how are any of these objects helpful in actually making the visualizer? Well, first of all, this is the audio that we're going to be visualizing. As to how to visualize it, we're going to be using an object that I mentioned at the start of the video, the audio analyzer. So for this object, I'm going to add a brand new part just for the sake of separating all the other ones. Just to clarify, you don't actually need any separate parts for any of this. You just need to have one single part in which you can have the audio emitter inside. The audio player, the audio analyzer, the wires, they could be anywhere. For example, I could just remove that, but I'll keep it in this case, just to make sure that you guys understand this a little better. Now we're gonna actually add the object itself, which is the audio analyzer. And we'll also add a second wire because now we'll need to connect this audio analyzer back to the audio source. As I explained before, you can actually have multiple different parts of an audio circuit in parallel. On one hand, we're going to have the audio emitter, which is going to be outputting the audio, and we'll have the audio analyzer, which will just be analyzing the entire time. Now it's time for me to showcase what this thing can actually do with yet another script. As usual, run contact set to client, and now I'm just going to create a variable that's going to represent the audio analyzer. So there's two main useful things this can do, and we'll start off by showcasing its ability to display the max loudness experienced in the last audio buffer. The last audio buffer is simply just the last time that the analyzer analyzed all the frequencies and loudnesses. As an example here, I want to print the peak level of loudness in the last audio buffer every 1 second. So let's see how this works by looking at our output. As you can see, we've started to get values that are between 0 and 1 that represent the peak loudness of the song in the last audio buffer. Now, to be honest, this was not the most useful feature of this analyzer, and you obviously know why I'm here making this video in the first place, and that's the frequency analyzer feature. So to actually get all the frequency bands, we'll use analyzer : get spectrum. Now to quickly explain what the bands are, the 512 frequency bands, as they call them, is just 512 different points in between the frequency 0 and 24,000 Hz. So it's just 512 different sections. What get spectrum does is it gets the loudness for each one of those bands in the last audio buffer. Now, if we just go back to test this out, you're going to see we'll have a giant table printed into our output, which we'll browse through in just a second. As you can see, we have a giant table full of different values for every single frequency band out of the 512 bands we have available to us. In the next video, I'll be explaining the importance of each one of them and how to use them to your own advantage for more advanced visualizers. Now that we know how all of this works, we can get started on a scrap visualizer. Just something to understand how this all works, and just a proof of concept in general. So in this video, I will not be showcasing a mapping feature, which is something that I'll show in the next part of all of this, since I don't want to make the video too long. Because we don't have a mapping function in this case, we'll have to make a part for every single one of the frequency bands. We can do this using a for loop, as you can see right here. All we'll do here is we'll just use instant.new to get a brand new part and just set it up in a way that we can arrange it with all the other ones. Don't forget to parent this to workspace by using game.workspace after the string part. To keep track of all of these bands that we've created in order, we're going to make an empty table before the loop in which we're going to be inserting everything. To actually insert all of this into the table, we'll use the table.insert function, and we're going to set the first value as the table we're inserting into, in this case bands, and then what we're inserting inside of it, in this case the instance new part. At the start I messed it up, but you'll see in a second that I corrected it. Next up, we'll make a similar loop that is going to control all the different sizes of every single band. Since the getSpectrum function returns us 512 elements in a table just like the parts that we have at the start of the script, we can actually just correspond the same number to the same value. What I mean by that is that when we have, for example, the first part of the table that we made at the start, we can associate it to the first value in the table from the getSpectrum from the analyzer. For the sake of ease, I'll make a variable for the spectrum. That way I don't have to call the getSpectrum function every single time I want to get the spectrum from that moment. So we don't actually need this print statement anymore, so we'll remove it, and we'll change the 1 inside the task.wait to a blank, since we don't want delays between every single time we check the bands. Finally, we'll be using this line of code to change the part size to something that's going to correspond to the loudness of the corresponding band. Before that, however, I forgot to actually make the part of the script that's going to arrange the parts in an order that's going to showcase them from the lowest frequencies to the highest frequencies. So the way we're going to do this is we'll just be switching the part position to a brand new vector3 value, which will be controlled by the I variable. If you didn't know, the for I loop in Lua, what it does is it takes the I variable and keeps adding 1 to it until it hits the upper bound limit, which in this case we set to 512. In this case, I just want it to be offset by 1 stud every time on the x-axis, so I replaced x with the I. Please ignore what I wrote here, since I learned after a future mistake that this was just me misreading. The bands do not in fact range from 0 to 10 in intensity, but they range from 0 to 1. Finally, to make the size change, we can just access the value I in the spectrum table, just like we access the value I in the bands table at the start of the line that I'm writing right now. In just a second, we're going to cut to a future version of the script because I had a few errors along the way, and I'll be explaining what they are. Here, I'm multiplying it by 2, but we'll have to multiply it by a lot more. However, I kept this mistake in because this is a learning moment. Since sometimes some bands will just be completely inactive, they're going to return blank values, and if they return blank values, multiplying them by 2 will cause an error. So here, we can do a check if statement to see if it's nil or not. At the moment of writing this, I forgot that the not equals function existed, so instead I made an if statement checking if it is blank, and then adding a print statement saying that it's blank. Now here's the cut into the future. I'm just going to freeze frame this to explain what I did. The only things I changed here is I added a line over on line 8 to make sure that the parts are anchored in place. Then I added a proper if statement check to see if the values are not nil before changing them in size. Otherwise, the script is identical, and ignore the test variable because it serves nothing. Here's the final test. This video is almost 20 minutes long, and I don't want to stretch it out for longer than it has to be, so I'll conclude the video here, and on the next part of the video, I'm going to show you guys how to actually implement this into a practical visualizer, including a chromatic style visualizer and a burst effect kind of thing. Thank you so much for watching, and I'll see you in the next video.